All right, well, I can't put it off any longer here, so let's start taking a look at how to use Kirchhoff's laws to analyze more complicated circuits. So I'll give you a bit of a step-by-step here first. And I'm going to say the first rule of using Kirchhoff's laws is don't use Kirchhoff's laws. And the second rule of using Kirchhoff's laws is don't use Kirchhoff's laws. Okay, that's maybe just a little bit too strong, but I'm trying to put a bit of an impression in you. I view using Kirchhoff's laws to analyze circuits in physics to be sort of an in case of emergency break glass kind of thing. So let's soften down the first two rules of Kirchhoff's laws just a little bit. We'll say try to be clever and avoid Kirchhoff's rules. Avoid Kirchhoff's laws. For instance, mapping potential zones. Can sometimes give you an awful lot of bang for the buck without having to do the full-on calculations, because although setting things up is pretty straightforward, and whenever I'm writing tests, I generally don't expect people to be able to solve more than 3 equations at once. But and if it's more than that, I generally will just ask that people set it up or something like that. The actual solving gets a bit tedious. So that's the main reason why you want to avoid it. So a little extra effort into thinking about the physics of the situation can sometimes avoid trauma later. And here, despite everything that you've heard and seen me do for all the videos up to this point, I will say reluctantly, it's okay to put numbers in right away. But only for Kirchhoff's laws situations. And why do I say that? Now I'll put in the caveat, but be careful. The main reason I say that is that these equations get to be such a mess that regardless of whether you do it symbolically or if you stuff the numbers in right away, when you mess up the algebra, you're never going to find where you made the mistake, and you're going to have to start all over either way. So if you want to leave it as symbols, go ahead. If you want to go ahead and stick in numbers, I'm not happy about it, but it isn't going to make a whole heck of a lot of difference. All right, so if you are going ahead and insisting on this, some of this will make more sense once I work an example, but I'm just kind of putting it all out here now. The first step, the first step of actually doing Kirchhoff here is to assign your currents. Yeah, I can spell IGN. And I'll just say try to use your intuition to guess the currents. To guess current directions. But even with a lot of experience, probably gonna not always get it right. And that'll be okay. So guessing wrong is okay. wrong, you'll just get a negative number. When you solve. Now, the important thing here is that sort of the penalty for guessing wrong is when you substitute, you have to carry that minus sign along. So all it means, if you guess wrong, you get a negative number. That just means that the actual physical current flows in the opposite direction of what you assigned, but the system of equations that you built up will be built around that incorrect guess. So when you put in for everything else, you have to carry the minus sign in order to make sure that all of the other currents work out. So the big deal is you need to get as many equations as you have unknowns. And as a general rule of thumb, node equations are more straightforward to use than loop equations. So we want to write as many node equations as we can. And the first step there is always going to be to count your nodes. And you write down one fewer equations than the number of nodes you have. Now, the reason for this is, let's say you're analyzing a circuit and you count that you have 17 nodes. You might be tempted to write down 17 node equations, but you shouldn't. You should only write 16 node equations in that case. And the reason is that the 17th equation, it doesn't matter which one, any of the 17 possible node equations you can have turn out to be what you have if you add up the other 16. So in order to have what mathematicians call a linearly independent system, you cannot write down that last equation. Because what can happen otherwise is you'll go along and you'll be substituting, and then all of a sudden, absolutely everything cancels and you get 0 equals 0, which is a true statement, but isn't I3 equals 4 amps or something like that, which you were hoping to have happen. So if you want to avoid that disaster, resist the temptation to write down the very last possible node equation, stop one short, and you'll be good. Now, in almost any situation, once you've written your down all of your node equations, you still will not have enough equations, because remember, when solving simultaneous equations, you always have to have as many equations as unknowns. So then this is where we add in the loop equations. So we add enough loop equations until the number of equations equals the number of unknowns. And keep track of that, because sometimes you can run into situations where as you keep adding equations, you find that your number of unknowns is going up too. So just because you counted all of your unknowns to begin with doesn't mean you might not end up with a few more. So you're going to have to keep the process going. And again, you run into the same problem. There are more possible loop equations that you can write than are linearly independent. So this is how I do it to make sure that you always have a set of equations that are linearly independent, so you don't get that mass cancellation and 0 equals 0 business. Other people have other techniques. There's one technique where you do all the loops, every possible loop you can write goes through the battery. That has the advantage that there's a battery EMF everywhere that you can cancel. I don't do it that way because I find that I get a little confused. So I do the other popular choice, which is to say the first loop goes through the battery. And it's the smallest loop you can draw that involves the battery. And then for subsequent loops, I follow the something old, something new rule. Oops. So what do I mean by that? What I mean by that is that any additional loop that you draw must go through something you've gone through before and something that you have not gone through before. If a loop that you draw goes only through items that you have gone through before in previous loop law equations, then it turns out that that loop is going to be equal to the sum of some number of those equations. Again, you lose your linear independence, and as you go along and solve, suddenly everything's going to turn into 0 equals 0. And again, in order to avoid clutter, and it's going to be kind of unavoidable, but to minimize clutter, try to keep your loops small. So then once you've done all that, what step are we on? Step 6. Solve using your favorite technique. So if you've had some exposure to linear algebra, then by all means, go ahead, set up the augmented matrix and reduce it. That's probably going to be the easiest way to do that. And you can kind of just quickly go through what I'm about to present next. Now, if what I just said sounded like so much pig Latin to you, let me show an example of how to organize your algebra to keep from being confused. So let's go ahead and work an example. So this is one of the smallest possible circuits that I can draw that is going to have to be solved by Kirchhoff's laws, and we can't do it any other way. So let's say I have here a 10-volt battery. There we go. So we'll say E1 is 10 volts. We'll say this is a 1 ohm resistor. We'll say this is a 2 ohm resistor. We'll say this is a 1 ohm resistor. We'll say that this is also a 1 ohm resistor, and we'll say that that is also a 1 ohm resistor. And we'll say that this is also a 10-volt battery. Now, what I would like to know is the current flowing through literally everything in the circuit. So let's go ahead and assign our currents. Now currents can change whenever you hit a node. So in this branch right here, there are no nodes. If I were to run my finger through, there's no junctions here. So no nodes. And we can use, looking at this, you can tell that this is going to be going clockwise and this is going to be going counterclockwise. But I'm going to intentionally make a bad guess along the way just to show that the world doesn't come to an end if you guess wrong. Now here we're going to guess right, and we're going to say that this current I1 is flowing through this chunk of the circuit, I1, clockwise, and that's also up through the battery. Now here with this junction right here, I can't assign I1 to this bit here. And again, as an aside, if in some previous life you have heard about a thing called mesh currents, you have my blessing to use that, but I'm not going to present that here. So I'm going to say that this current is I2. Now, from the symmetry of the situation, we can guess that this is going to be flowing counterclockwise, but let's say that we were just having an epically bad day with our guessing, and we guessed that the current flowed clockwise. So spoiler alert, I3 is going to end up being a negative number when we solve for it. But I just want to show that the world doesn't come to an end when that happens. So we've assigned all of our currents, and we were asked to find what is I1, I2, and I3 equal to. So since we have three unknowns, we're going to need three equations, and there's always the possibility that more might come in as you add equations. Sometimes you bring in additional unknowns. That's not going to happen here, but at least as a starting point, we know that at bare minimum, we need three equations. So we go ahead and follow our first rule here, which is to try to be clever and not use Kirchhoff's rules. Unfortunately, that isn't going to work. One way we could be clever is if we recognize some things in series or parallel. Okay, this is in series, that's in series. That helps a little bit, but not really. The big issue here is that this is not in series and that is not in series. And although if you map the potential zones, although the voltages will all be the same, the potential zone colors won't match, and so we don't have anything in parallel here. So doing this by attempting to be clever is probably not going to work for us. So this is one of those emergencies where we need to break the glass and use Kirchhoff's laws. So with that, we go ahead and count our nodes. One node, two nodes. So since I have two nodes, that means I can write exactly 2 minus 1 equals 1 node equation. It doesn't matter which node I pick, they're going to be the same. So let's go ahead and do it for that node up there. So for our node equation, we are going to have the sum of the currents in equal the sum of the currents out. So what we have going in. So remember, it's not what's actually physically happening, it's what we've assigned mathematically. And if we get it wrong, negative signs will happen to fix everything at the end. So the way it's assigned, I1 is the only thing flowing in, and I2 and I3 are both flowing out of the node. Oops, I2 plus I3. We could have chosen this node just as easily, and all that would have happened is you would have had I2 plus I3, the currents going in, equals I1, the currents going out. So you can see, if I wrote both node equations, I would have the same equation twice, and if I tried substituting in, everything cancels out, and that's generally not a happy thing. All right. So we've written all the node equations we can possibly write. So our next step is to write loop equations. So we will start by identifying our loops. So I will start in the lower left-hand corner, go through the battery. This is the smallest loop I can draw. So I'm going to draw that one, and I'm going to call this loop number 1. So our equation for loop number 1 is, well, let's see. I walk my imaginary dog along here. I leave this battery at the positive terminal, so this will be plus 10. And what the heck, I'm not even going to bother writing the units for exactly the same reason. If I mess up the algebra, it's all going to go to Hades anyway. All right. So here I write minus, well, I times R1, the resistance is 1. So this is minus 1 times I1. And here, gotta be careful. This now here's I2 right here. Oops, don't want it in that color. So remember, just that was I2 right there. So, and this is 2 ohms. So this will be minus 2I2, because I am at least going with the current. So this will be minus 2I2. Now I'm back here. Once I go through this branch, I'm back to I1. So this is minus 1I1. And I'm back home, so that's equals 0. All right. Now I need to draw another loop equation, and some people, when they show this, they'll say, "Oh, just make the next bigger loop around." If that gives you joy, go right ahead. For me, as a matter of personal preference, I found that got a little confusing. So what I do is I will start here and go around like this. So this is following the something old, something new rule. It's going through this resistor I2 that we've done before, or R2 that we've done before. But it's also going through all these elements that we have not gone through before. Now notice at this point we have drawn loops on that go through literally everything. So the other loop equations that you could possibly write, and believe it or not, there are 2 more. You could do this outer loop, and you can even do this sick and twisted figure 8 kind of thing. Those are both valid equations, but both of those will end up giving you the exact same thing you would get if you just add these 2 loop equations together. So they're not linearly independent. So when we write down this loop equation, we are out of loop equations, and we better have enough equations to solve for all of our unknowns, or else we are in big trouble. So let's write down our equation number 2. So as I walk my imaginary dog along here, the first thing I do is I go against this resistor here. So I'm going against the current. So this means that we will get increase by 2I2. So I'll write a plus 2 I2 here, and you can see those are opposite signs. That'll create a nice convenient cancellation. That's part of why I'm a fan of the something old, something new technique. Now here I'm going with my assigned current I3. So I write minus 1I3. And then here I am going, I enter the battery on the positive side, I exit on the negative side. I always pick up the sign of the terminal I exit. So that's minus 10 volts, or we'll just write minus 10. And then finally going with I3 through R5, this will be minus 1 I3, and I walk my imaginary dog back home to write equals 0. So that is my system of equations. So I have 1, 2, 3 equations in our 3 unknowns, and we've done them in a way that guarantees that they're linearly independent. So now what I'm going to be doing is just presenting a way to organize your equations for larger systems of equations like this in a way that will make them a little more tractable. So I'll start by writing my node equation here. What I'm going to do is I'm going to put all my currents on one side, and if I have any constants, they're going to end up on the other side of the equation. So this will be I1 minus I2. And you'll notice I'm leaving good amounts of space here. This is just to keep things decluttered, equals 0. So that's this first equation here. Now this equation here, if I add the i's to both sides and divide through by 2, so yes, I'm skipping a couple steps, I'm sorry, but it'll be helpful because this is going to be negative 2 I1 here. I got negative 2 I2. So I'll just divide through by 2. This 10 will become a 5, and then we will be left with I1 plus I2. And I would leave a space where this I3 is to write equals 5. And then finally, for this one, I will go ahead and I'll add 10 to both sides, and then I have a minus 1 I3 here, minus 1 I3 here. That's negative 2 I3. Divide through by 2, I will have I2 minus I3 equals 5 there. Now, if this were just a 2 by 2 system of equations, I would just say, hey, solve for one, substitute into the other, or solve them both for the same thing, set them equal to each other, or whatever technique your high school algebra teacher showed you. But when you get to systems of, and you can even get away with that with systems of 3 equations, but when you get to systems of 4 and more, what becomes a lot easier to do is just plain start adding equations together. So let's go ahead, add or subtract equations. You might multiply them by some multiply through by some constants. That's totally cool too. So for instance, if I take these two equations here, what that will do when I add these two is the I2s will cancel. So then I'll just have an equation in I1 and I3, and this will be in I2 and I3. And then I can go ahead and eliminate I3 between what's left to get I2. So, let's go ahead and do that. So first I will go ahead and add these two equations together. This will give me 2 I1. And then adding this and this is going to give me just plain nothing. Then adding this is going to give me minus I3. And then adding these two is 0 plus 5 equals 5. And then I'll carry through what I had before, I2 minus I3 equals 5. All right, so at least I can get something here in terms of, so if I go ahead and look at this one and this one, I can go ahead and subtract those two from each other. So let's do that. I'll have 2I1 minus I3 equals 5. And I can take this and subtract. I will have I1, those two cancel, plus I3. Subtracting those, 5 minus 5 equals 0. All right. Now, finally, I can add these two equations. So adding these two equations gives me 3I1 equals 5. And so I1 equals plus 5/3 of an amp. Yay. Now that I have I1, this equation here will immediately give me I3. I get that I3, from that, I immediately get that I3 is equal to negative I1, which is negative 5/3 of an amp. Oops, I have a minus sign there. What does that minus sign mean? It means going way back here when I guessed about the direction of I3, I was wrong. I3 really flows the other way. So we will even go ahead and, just to help keep some sanity, we will note that I3 really flows like this. Oops. But when we substitute the I3 in, we have to keep the negative number because we guessed wrong. And our system of equations is built on that bad guess. So we can just use this I2 minus I3 equals 5. Sure, that sounds good. Let's do that. So from I2 minus I3 equals 5, we get that I2 is equal to 5 plus I3, right? Yeah, right. I2 minus I3 is 5. Yep. So now we will go ahead and put that in. So this will be 5 minus 5/3. So that's 15/3 minus 5/3 is plus 10/3. Whoops. Is plus 10/3 of an amp. So that means that we did guess the direction of I2 correctly. Now, like I say, if you've had linear algebra and you know how to set up matrices and reduce them, by all means do that. That'll be certainly a faster way to go. Now, I think it would be worthwhile to go take a look at another application of using Kirchhoff's rules. So I'm going to draw the basically one of the simplest networks of resistors you can have that cannot be analyzed by reducing them into smaller series and parallel pieces. So so we got 1 ohm there, 5 ohms there, 1 ohm here. And what I want to know is, what is the equivalent resistance of this network? And the problem here is that we literally don't know. We can't break it down by series and parallel. You can run your finger through anything you want here, and it's not going to, you'll always pass through a junction. You can't find any two things that you can go through that don't go through a junction. So there's nothing that reduces in series. Similarly, if you map out all the color zones, which I'm not going to do because I don't want to clutter this thing to oblivion, you will find that nothing has the same pair of colors. So there's literally nothing in parallel. So there's nothing in series, nothing in parallel anywhere in here. So it turns out the only way we can find the equivalent resistance is to resort to using Kirchhoff's laws. And the way we do that is we add in an imaginary battery, like so. And we'll just say it has an EMF of EMF. I'm not a fan of making up a number here, but I guess if you wanted to use one, go ahead. But anyway, whatever it is, we pretend we know this. And remember, when we're talking about equivalent resistance, what's going to matter is to the battery is how much current is going through it. So I will cryptically call this I6, so I stay consistent with my notes. And the end game here that we're going to have is we're going to solve to get E equals something. I'll just call that box times I6. And the thing that whatever it is that's in front of the I6, we're going to identify that as the equivalent resistance, because the battery doesn't know that there's a whole network here. It just knows that I6 is passing through it. So an equivalent resistance that would pull I6 through this would be the same difference to the battery. All right. So with that, let me go ahead now and label my other currents. I will call this one I1, this one I3, I'm calling this one I5, this one's I4, and this one is I2. And the only thing motivating these guesses in the least is that I know that there's going to be a general clockwise thing and happening here, and honestly I am just taking a total guess as to which way I5 is flowing. I've got no idea. All right, so since we've got more than two nodes here, let's go ahead and label nodes. So I'll call this node A, node B, node C, node D. So having labeled them, we can also already tell we have 1, 2, 3, 4 node equations. So since we've got 4 node equations, that means that we can write 3 of them. So 4 nodes means 4 minus 1 equals 3 node equations, and we want them all because they're easier to use. So let's go ahead and write them. So it doesn't matter which 3 we pick. The fourth one will be equal to the sum of the other 3. So I'm just going to pick A, B, and C because they're the first 3 in the alphabet. So node A. So what we got going into node A? We've got I6 going into node A. Actually, let's draw a little box. So we got I6 going into A, and we have I1 and I3 going out of A. So I6 going in, and I1 and I3 going out. So current in equals current out. All right, let's do node B. So for node B, I've got I3 and I5 going in and I4 going out. And by the way, when you're signing these currents, sometimes you can do so bad in guessing, and you're not a bad person if this happens or anything, that you can have them all going in or all going out. That's okay. You just put a 0 for the other side of the equation. And then obviously at least one of them's got to be negative. All right, and then let's look at node C. Node C, we've got I1 going in and I2 and I5 going out. All right, so then that's it for node equations. And if we go and take a look at this, what do we have? We're trying to solve for the EMF. Actually, we pretend we know I6 would be a better way to think about it. We're trying to solve for the EMF in terms of I6. So the EMF is one of our unknowns. I6 is known. Then we have I1, 2, 3, 4, 5 are unknown. So we've got a grand total of 6 unknowns. This means we need at least 3 more loop equations. Maybe more, but we won't, fortunately. All right, so same deal. I make the smallest loop I can that goes through the battery. That will be my first loop. So again, I always start in the lower left-hand corner, go around, clockwise. And again, that's just purely personal preference. This is loop number 1, so let's write that loop equation. So when I walk my hypothetical dog along, I'm going with the current here, so minus 1I1 minus 1I2 plus the battery EMF, because I exit the positive terminal, equals 0. So 1I1 plus 1I2 minus the battery, minus 1I1 minus 1I2 plus the battery EMF equals 0. All right. So now we follow the something old, something new rule, and we try to keep our loop as small as possible. So, I mean, I could draw this one, but that wouldn't be the smallest thing possible, and that would just make it cluttered. It's valid, but it's just, I'm trying to avoid clutter here. So here is my loop number 2. So again, starting in the lower left-hand corner and working my way around, this will be minus 3I3 here. Now here I'm going against the current, so this will be plus 1I5 minus 1I1. I get back home, I write equals 0. So loop number 2 will give me, minus 3I1 plus 1I5 plus 1I1 equals 0. Okay. So again, following the something old, something new rule, this will work. So there's my third loop right there. And now we are going to be done with loop equations because we've gone through literally everything. Once you've gone through literally everything, you are out of loop equations, and you better hope you have enough equations. In this case, we will. So walking my imaginary dog along here, this will be minus 1I5 minus 5I4, and then I'm going against the current here, so plus 1I2, and that's going to equal 0. So minus 1I5 minus 5I4 plus 1I2 equals 0, and there is my system of equations. And if you think I'm going to go and solve all 6 of these by hand in this video, you're nuts. Now, I have gone and done this by hand because I'm nuts, and it only took me about 3.5 pages close packed on a legal pad to do it. The EMF is 27/17 I6, and so we identify this as being our equivalent resistance to get that the equivalent resistance is clearly 27/17 ohms. So that's how you handle a system that's neither series nor parallel, and you would use the same kind of, you can try to use the same sort of trick with capacitors, but certainly for when you got networks of resistors that are neither series nor parallel, this works really well. Capacitors, they can get a little dicier. All right, so with that, go ahead and have a good one. Catch you later.